Okay, so let me start by quickly describing what this workshop is about. Okay, so of course you all sign up because this is about difference in differences. So hopefully you have at least a vague idea of what this is. So difference in differences methods have become extremely popular as a tool for causal inference and policy evaluation. And there's many reasons why they have. So some of the reasons that I think explain the very high popularity of diff-in-diff is that, first of all, it's a non-experimental method that can be used with observational data. Okay, so I'm sure you all know it's great when you can randomize a treatment or a policy because that really solves a lot of problems. But in many cases, you can't, right? There are many policies that cannot really be randomized, either because it's logistically too difficult, or maybe politically infeasible, or maybe morally questionable. There's many reasons why, in many cases, we cannot really randomly assign treatments. And so we need to use observational data. And diff-in-diff is one tool that we can use in this type of settings under some specific assumptions, of course. So that's, I think, one reason why diff-in-diff is very popular. Reason number two is actually it's not very demanding in terms of the data that it requires. Okay, so in its simplest setup, of course, the more data you have, the better, always. But in the simplest setup, a diff-in-diff requires basically observing some outcomes over time for a group that is affected by the treatment and a group that is not affected by this treatment. Okay, before and after the treated group is actually affected. Okay, so in fact, in the most minimalistic case, you need kind of like 4 data points to be able to estimate a treatment effect using diff-in-diff. Okay, so for example, diff-in-diff, again, in its simplest setup, does not require, for example, additional covariates. Okay, so we know there's other methods, like, for example, say propensity score matching, where you know that you need a very large set of covariates that would explain who gets treated, who doesn't get treated, to account for selection bias. In diff-in-diff, in principle, we don't need additional covariates. We can use additional covariates, and we will discuss how to do that later on. But in principle, covariates are not required. And also, diff-in-diff methods are usually easy to implement with just administrative data, and which is something that is coming increasingly available, right? So it's easier and easier as the computational power increases and people become more aware of how important it is to do data analysis for policy evaluation. Now it's fairly easy to go on like a government website or something like that and download county level data or state level data over time and information on which counties or states are affected by a certain policy and so on. So again, one of the reasons why I think diff-in-diff is very popular is because it's not really very demanding in terms of the data that one needs. And the third reason is that diff-in-diff methods are actually pretty simple to estimate. Okay, so they can be estimated based on linear regression, which is something that we all know and understand, and the software can do very well. Okay, so we will briefly discuss, without getting too much into the details, that estimating a diff-in-diff, or more generally a two-way fixed effects model, is basically running a linear regression on after transforming the data in some appropriate way. Okay, so again, 3 reasons why diff-in-diff have become very popular. They're non-experimental, they're not very demanding in terms of data requirements, they're easy to estimate, and also I should add here, they work under some assumptions that we kind of understand pretty well, and that also can be represented visually. So a good diff-in-diff can be very compelling as an estimator for the effect of a treatment or a policy. And of course, this is all these are all things that we're going to discuss in detail throughout the course. So just to show you that what I'm saying is true, this is a couple of graphs from a paper by Curry, Cleven, and Swigers, where they basically use text analysis to show what methods are, or the popularity of different causal inference methods this is only in economics, okay? So my background is in economics, so you're going to see that most of the examples come from econ papers, but I'm sure this is true in other disciplines as well. So in panel A up here, you have basically the fraction of papers in economics that use difference in differences. And so you have 2 curves here. The first one is the NBER working paper. So NBER is the National Bureau of Economic Research. So NBR working papers are a very popular kind of like repository for working papers, one of the most prestigious ones, I would say. And then the second line is just the papers in top 5 journals in economics. Okay, so you can clearly see that starting, I guess, around 1994, maybe, could be Carden-Kruger's paper. This shows a pretty clear increasing trend, or a pretty clear increase. Okay. Also, let me check. There's something in the chat. Okay, no. Okay, so a pretty clear increase in the number of papers using difference in differences, and so this goes to 2020, and I'm sure this has kept increasing in the following years. And then same on panel C, which is the third graph in the paper, but second graph here, where they count the number of papers that use event studies. And event studies, as we will see later on, is just a different way to do diff-in-diff. Basically, again, very clear increase in the past maybe 10, 15, or 20 years. Okay, and as I said, this is in economics, but it's also true in political sciences, in health sciences, in education, and many other fields. Okay, so we've been doing diff-in-diff for maybe 15 years, and we're all very happy with it. But then recently, a group of econometricians and methodologists and other party poopers have been looking at diff-in-diff, and actually found that it turns out that diff-in-diff models don't always work as we thought they did. Okay, and so this literature has pointed out 2 main challenges to diff-in-diff models that basically, when they combine, they can make the diff-in-diff models fail. Okay, so these 2 challenges that are pointed out by the literature are, number 1, non-simultaneous adoption of the treatment. Okay, so what do I mean by that? Well, in its canonical simplest form, a diff-in-diff basically compares 2 groups, one that is subject to some treatment or policy after some time period and not before. So that group is compared to another group that is never subject to this policy. Okay, so we basically compare what is the change over time in the outcome before and after this policy for the group that is affected by the policy, and compare that to the before-after for the untreated group. That's the simplest diff-in-diff case. Now, in practice, in many situations, that is not exactly what happens. Okay, so instead, what we have is multiple groups, and different groups are entering treatment at different times. So a policy affects some units in, say, year 2010, some units in year 2012, 2015, and so on. Okay, so this is what we call non-simultaneous adoption of the treatment. Okay, and so, by the way, absolutely, you can all interrupt whenever you want. Okay, so if you have questions, please either raise your hand or just unmute yourself and go ahead. Okay, I think somebody asked in the chat. Okay, so I was saying non-simultaneous adoption of the treatment. Actually, later we're going to call this staggered adoption of the treatment. That's challenge number 1. And challenge number 2 is treatment effect heterogeneity. Okay, what do I mean by that? Well, you know, whenever there is a treatment assigned to a group of people, it is very likely that this treatment will have different effects on different units. Okay, so some people may benefit more and some people may benefit less from this treatment. And not only that, but also in diff-in-diff methods where we follow units over time, we may also think that the treatment effect changes over time, right? So there may be many policies where maybe, you know, the effect in the first time periods is kind of small and then it increases, or maybe the effect is very big in the beginning and then fades out, and so on. Okay, so this is what we call treatment effect heterogeneity. And so we will see that the combination of these 2 factors of treatment effect heterogeneity and non-simultaneous adoption of the treatment will generate problems for the diff-in-diff. And so then if we just estimate the effect of a policy using a diff-in-diff in such setups, we may get misleading conclusions. Okay. Okay, so question in the chat, can the treatment be in different intensities? Okay, so yes, it can. In most of this workshop, we will focus on the simple case in which the treatment is binary. Okay, so we're going to say just like affected by the policy, not affected by the policy. Okay, so most of these slides will be on binary treatments. The question of how diff-in-diff models work with continuous treatment is an open one. I actually have a paper right now that I'm working on continuous treatments with diff-in-diff, which adds kind of like an extra layer of complication. So actually what we'll see is that even in the simple case with a binary treatment, diff-in-diff models can fail in some settings. And then if on top of that, you add the fact that maybe your treatment is not binary, so it's not even clear what you mean by the treated and the untreated group, that can be even worse. Okay, so maybe if we have time, we'll discuss that by the end of the class. But for now, we're going to start with the easy case of binary treatments. Okay, and so in the chat, Asil is saying, for example, if different countries receive different numbers of refugees as a treatment, that would be a great example of a non-binary treatment, right? Because the number of refugees could vary across different states or counties and so on. So in some settings, we may, for example, just to simplify, we can make the treatment binary, but if we have, for example, states that do not receive any refugees and some states that receive, high or low numbers of refugees, so you can kind of like discretize that treatment. Again, it's a great question, and I'm happy to discuss it later on. But for at least for the first set of slides, let's think about the easy case. Okay, so if you're working on a paper about the effect of refugees, for now, just think about the case in which you have some states or counties that receive 0 refugees and some states or counties that receive more than 0 refugees. Okay, and again, I'm happy to discuss this more by the end of the class, okay, or of the workshop, because it's a very interesting question. Okay. Okay, so I was saying we have been happily using diff-in-diff methods for 15 or 20 years, and then suddenly, just a couple of years ago, and so these papers are very recent. Most are for like 2020, 2021, or 2022, showing that actually diff-in-diff may not work as we expected, and this has created a lot of confusion. Okay, so these papers are technical, they're hard to read, and so now applied researchers know that they may be problems with their diff-in-diffs. Nobody knows exactly why. Okay, so you know that if you're presenting a paper using diff-in-diff, somebody in the audience will say, oh, but are you aware of this recent literature showing that you may have problems? And so it's like, yes, I know there is a literature showing that there's problems. Maybe I don't know exactly what to do about it. So if that is the case for you, you are in the right place. Okay, so the goal of this workshop will be to understand first the assumptions behind a diff-in-diff and how diff-in-diffs work. Okay, so how do we estimate treatment effects using diff-in-diff? What assumptions do we need? Number 2, we're going to discuss in detail when the diff-in-diff can work, and then when it does, how to support its validity. Okay, because as you know, if you write papers or projects using diff-in-diff, it's not just a matter of saying, I'm using diff-in-diff, here are my estimates, here are my t-statistics. Okay, so you actually have to make the case to convince the reader that what you're doing is correct. Okay, and there's a bunch of tests and strategies that one should consider to kind of like check that the diff-in-diff is working as it should be working. Okay, so that will be the second goal of this course. Number 3, like I just said, there are cases in which diff-in-diff may not work, and so we want to understand what cases, what those cases are, and then in that case, what can be done. Okay, so if we run into this issue, maybe where we have a setup with staggered adoption of the treatment effects heterogeneity, and we suspect that diff-in-diff may not work well, should we just like not work on that project, or is there anything we can do? And of course, the answer is like, yes, there's a lot of stuff that you can do, and we will discuss that in detail. And obviously, number 4 is like, okay, now that you know what you have to do, how do you actually do it with your data set? Okay, so we're going to discuss how to implement what I call classical methods in diff-in-diff, and also these novel methods that have been proposed in the past couple of years that deal with these problems about treatment effect heterogeneity and maybe staggered adoption and so on in R and Stata. Okay, so that I would say is the some of the goals of this course. Just to give a quick outline of the topics that we're going to cover, I'm going to start with what I call a quick review of linear panel data methods. Okay, so you're going to see part number 1 is kind of like a textbook treatment of panel data methods. Okay, so if you studied econometrics or statistics, this may sound familiar. Okay, and so I'm going to do this just kind of like to warm up a little bit and try to motivate why we want to use this difference in difference methods, which in terms of estimation is just like one particular case of what we call two-way fixed effects methods. Okay, so I'm going to start with that to make sure that we're all on the same page. After that, I'm going to move on to introducing potential outcomes and diff-in-diff models. Okay, and so potential outcomes is not the only one, but a very popular framework to analyze causal effects or treatment effects. Okay, so you'll notice in part 1, when I talk about panel data methods, I'm not really going to talk about causal effects. I'm just going to say, we want to estimate this regression. We want to estimate this parameter from a certain regression. How do we do it? And then in part 2, I'm going to introduce potential outcomes because, you know, we're not just running regressions because we like regressions. We run regressions because we want to estimate causal effects. But the regression framework is not a good framework to understand what we mean by causal effect. Okay, so we will need to introduce some additional notation and a different theoretical framework to decide when is a regression estimate a good measure of a treatment effect or not. And within that context, I'm going to introduce diff-in-diff models in their simplest case, or what we call it 2x2 diff-in-diff model, to see how or under what assumptions a diff-in-diff can actually estimate or recover the causal effect of a treatment or policy. Okay, that will be part number 2. Part number 3, then we're gonna jump into the hardcore diff-in-diff. Okay, so we're gonna talk about first diff-in-diff under simultaneous adoption designs. Okay, this, as I said, is basically the canonical case in which we have two different groups, one that is never affected by a treatment and one group that is affected by a treatment after a certain time period. Okay, so for each group, we observe outcomes over time before and after a policy change or the introduction of a treatment. And then we're going to use this type of variation to try to identify the effect of this intervention. Okay, and so in part 3, we're going to discuss the easy case in which all the treated units receive the treatment at the same time. That is what we call a simultaneous adoption design. Okay, and after that, in part 4, we're gonna try to assess the parallel trends assumption. So maybe you've heard about this. So the parallel trends assumption is, we could say, one of the main identification assumptions behind diff-in-diff. Is kind of like the assumption that we need to impose to make sure that a diff-in-diff actually recovers a treatment effect. Okay, we're gonna discuss it in detail. So if you don't know what it is, don't worry. So this assumption is key for identifying the effect of a treatment or policy. Unfortunately, that assumption is untestable. Okay, so there's no amount of data that we can have that would let us test this assumption, because it requires information on stuff that we will never be able to observe. Okay, again, this may sound a little bit abstract so far. We're going to really look at that in detail. But the point in number 4 is that, okay, fine, this is an assumption that is absolutely crucial to interpret our estimates as causal effects, but also that we cannot test. So then what can we do in practice to make the case for it? Okay, so you may think that when you write a diff-in-diff, or actually when you write any type of paper based on any type of causal inference tool, you are kind of like a lawyer that has to make a case to a jury and convince that jury that what you're doing makes sense, so then that your estimates are good measures of this treatment effect. So in part 4 of the class, we're going to discuss several strategies to convince the reader that your diff-in-diff works. Okay. Next, in part 5, we're going to move on to diff-in-diff under what we call staggered adoption designs. As I mentioned before, staggered adoption designs are designs in which different units get treatment at different times. Okay, so if you think about this, say, the influx of refugees in different counties, And just again, let's think about the easy case in which maybe say like 0 refugees versus more than 0 refugees. There may be counties that get an influx of refugees in year 2015 and some other group of counties that get another influx in 2020. Okay, and we would like to compare this with some counties that maybe never receive refugees. Okay, but now we have variation in the treatment timing. Okay, so some counties are kind of like early treated, some counties are late treated. Okay, and as we briefly discussed before, this can generate problems for the diff-in-diff, especially in the case in which we think that the effects of the treatment may vary either across units or over time. Okay. And so we will discuss this part. So this is where all the problems are going to come up. And then we're going to try to understand why is it that diff-in-diff models may not work in this case? And of course, what to do if we think that these models are not going to work, and how to implement all these new methods that have been proposed by the methodological literature to deal with these problems and actually be able to recover credible estimates of policy effects under staggered adoption designs. And finally, in part 6, we're going to discuss a method that is not really diff-in-diff, but closely related to it, which is called synthetic control methods. So synthetic control methods are basically a tool that we can use to do case studies. Okay, so for example, a classical example in one of the initial papers on synthetic control is when, for example, maybe one state introduces a policy, for example, California introduced a policy to kind of like reduce tobacco consumption, okay, so cigarettes consumption. And so we want to see whether this policy effectively reduces tobacco consumption. But then we want to compare California to some other state or some other groups of states, but maybe these other groups of states are not really directly comparable to California because their outcomes follow different trajectories and so on. So in a synthetic control, what we do is we take a pool of untreated states and we try to construct what we call a synthetic control, which is basically a counterfactual for California. It's like what would have happened with California had California not introduced this policy. Okay. Again, all this may sound a little bit vague and imprecise so far. We're going to discuss all the details. Okay. What else should I say about this? First of all the topics that we discussed are going to be illustrated with empirical applications using real world data. Okay, so I have, and hopefully you have access to all the material. You have code and data sets from existing published papers, okay, using diff-in-diff. So we're going to kind of like replicate these papers and see how to implement all these methods. And so we're going to do all that. And then, of course, this is a workshop on statistical methods. So it does require some math. It requires, some notation, some formulas, etc. I'm an econometrician, so, I work with formulas and theorems. Having said that, I don't particularly enjoy doing math for the sake of it. Okay, I'm only going to use math to the extent that it helps either understand the intuition behind the methods or the assumptions behind the methods, or understand how to implement them in practice. Okay, so just a heads up is like there's going to be some notation, some algebra, some theorems, but I'm going to try to keep it to a minimum. Okay, focus on the intuition and the implementation. We're going to use software. Okay, as I just said, all the topics will be illustrated with empirical applications. I'm going to use R for this workshop. Okay, it has some advantages. For example, it's free. Okay, it's very popular, and so hopefully you've seen the syllabus of the class, and there you have instructions on how to download R and maybe RStudio and all the packages that we're going to use. You may also have noted that I provide Stata do files as well, and so these do files replicate the R scripts that we're going to do in class as closely as possible. Okay, this obviously not identical, but they basically do the same things. So if you're more comfortable with Stata, you're more than welcome to follow the empirical applications using the Stata do files. Okay, and you see that they have the same order, pretty much the same output. So if you prefer Stata to R, you're more than welcome to follow with the do files instead of the R scripts. I'm happy to answer questions whenever I can about either R of theta or theta. Okay. But then one caveat that I have to make, even though I said I will use R in the in-class applications, these are very recent methods, okay, which is kind of exciting, no? So like, but that also means that some of the packages we're going to use are actually being developed as we speak, okay? And so you will see that some of the packages that we're going to use are sometimes available in R, but not in Stata, or sometimes in Stata, or not in R, or sometimes they have been written by different authors, and so they don't exactly coincide, okay? That's a little bit unfortunate, but again, completely understandable, given that we are working on stuff. We're going to be discussing stuff that is like really being developed as we speak. Okay, so there may be a couple of cases in which I will need to move to Stata, or maybe just, you know, because some R packages are not available. And also, if you're following the Stata do files, there may be some cases in which some packages don't exactly replicate R, or maybe are not available in R. Okay, but I'll mostly mostly use R in the class. Okay, and finally, about class participation, I think somebody already asked this, but I strongly encourage you to jump in with questions at any time during class. Okay, so feel free to interrupt. You know, this is Zoom. We are kind of used to Zoom, also maybe a little bit tired. It's not obviously the same as being all in person in a class, but let's try to make this interactive, right? That's more fun, more lively. So feel free to either raise your hand on Zoom, or if maybe you raise your hand and I don't see it, just like unmute yourself and interrupt. You're also welcome to write in the chat, or sometimes I may miss the chat, but I'll try to monitor it. Okay, so again, you're strongly encouraged to jump in with questions, comments, you know, discussions, make the classes more interesting and easier to follow. Okay, so please interrupt whenever you want. We also have a Slack channel to post questions or comments, which I'll be checking sometime in the afternoon after the classes are over. But again, I encourage you, like, if you have, you know, questions or comments or anything, I encourage you to bring them to class whenever possible, so we can actually discuss, and it's not just like me speaking for hours and hours nonstop. Okay. So I think that's what I have in terms of class participation. So you have a syllabus that describes all this, and you should have access to all the slides, all the code, and all the data sets. Okay. Any questions about the class organization before I start with the actual material? Okay, no questions. So, you know, if you don't ask questions, I just keep talking, and, you know, I talk a lot. So again, you're encouraged to interrupt me anytime you want. Okay. The chat said, would we work in R as well? So yes, I mean, so you have all the code. So what I would suggest is, as long as you're comfortable with R, what I would recommend is just like open the code that I'm using, and just, you know, as I run the different lines, you should run them as well. So just to see like what you get in your computer. If you want, if you prefer to just like look at my screen and follow the code in you know, just like looking at my code, that's perfectly fine. And you have the code, so then after the class, you can just like go over it yourself at your own pace and so on. Or if you prefer to follow in Stata, again, it's just kind of like try to keep track of what I'm doing and how the do file does it. Okay. But so like, yeah, my suggestion would be like open the code at the same time as me, and then just like run it as we go. Okay. If there are no more questions, then we can start. As I said, the first thing I want to do, kind of as a warm-up, is a more textbook-like review of panel data models. Okay, so let's do that. First of all, what is panel data? Well, panel data is a data set in which we have data collected for multiple units, and by units, I mean, whatever your unit of observation is, which could be a person, a household, a county, a state, hospital, firm, whatever it is. We follow multiple units over multiple periods of time. Okay, so depending on your field or discipline, maybe you know this as longitudinal data instead of panel data. As I said, I come from an economics background, and we have our own terminology. It sometimes doesn't really coincide with terminologies in other fields, but the ideas are exactly the same. Okay, so then, panel data is kind of like the main requirement for diff-in-diff models. So we need to follow multiple units over multiple time periods. Okay, so basically, panel data is a combination of what we would call cross-sectional data, in which we observe a group of units at one specific time period. Okay, so maybe we have a survey done in 2015 of a bunch of households. That would be a cross-section. And then a time series is where we follow one county or state or household over time. Okay, so panel data is basically the combination of these two data structures. Okay, and we have two main features that panel data sets could have. One is what we call balanced panels. Okay, so in a balanced panel, we follow units that we're going to index by the letter I, and this will go from 1 to n. So n will be the total number of households or counties that we have, indexed by, and then time will be indexed by little t, going from 1 to capital T. This is just the time periods. That could be months or days or years or whatever it is. And so in a balanced panel, all the units that we observe are observed over the same time periods. Okay, so for example, maybe we have a bunch of surveys in 2010, 11, 12, 13, 14, where we follow counties. And so we have information for all the counties in all these time periods. Okay, that's what we call a panel, a balanced panel. So basically kind of like a rectangular structure. Okay, we see all the counties over all the time periods. In practice, in many cases, one has what we call an unbalanced panel. In an unbalanced panel, units are observed over different time periods. Okay, this could happen for a bunch of reasons. For example, maybe units enter or exit the panel at different times. And this could be either kind of like by design of the survey. So for example, there's a lot of like household surveys that maybe interview a household in year 1 and 2. And then to kind of like avoid bothering them too much, they leave them alone for 2 more years. And then they come back in years 4 and 6. Okay, so we have kind of like holes in where we interview different households. This is what is called like a rotating survey. So sometimes it's just like by design of the survey. In some cases, it's kind of like naturally happens. For example, if we're following firms over time, there are firms that are created and firms that disappear over time. So then we may have an unbalanced panel because some firms enter in different years, some firms drop out of the panel, and so on. Okay, so there may be many reasons why a panel may be unbalanced. In this workshop, we will focus on balanced panels. Okay, and in fact, we will focus on what we call a large n small t panel. What does that mean? Well, it's basically we're going to have kind of like many units over quote unquote a few time periods. Okay, so this is basically what you have when you work with micro data. Okay, so for example, maybe we have something like 500 counties followed over 5 time periods, okay, or something like that. Or maybe we have 10,000 households in 20 months or something like that. But basically the n dimension will be much larger than the t dimension in all the examples that we're going to discuss. Okay, again, the most common case when using micro data, in terms of theory, what this means is that whenever we talk about large samples, what we mean is having many units. Okay, so many households or counties or firms or hospitals or whatever. So basically in the asymptotic analysis, so in the large sample analysis, we're going to let n go to infinity with t fixed. Okay, So we're going to have a balanced panel, large N, small t, okay? And so in principle, we're going to have an outcome variable y, which is going to be indexed by I and t, okay? So yit will be the outcome for unit I observed at period t. And then we're going to have a regressor or an independent variable xit, okay? So again, the value of x for unit I in period t. If you want, you can make this x a vector, okay? So maybe you have a bunch of different characteristics for this unit, not really a problem, okay? And so we're gonna draw random samples of units. And so as we said, this is a balanced panel. So basically our data will look like this, okay? So for each unit I, we're gonna see the outcome in all the time periods, okay? So outcome in period 1, 2, 3, 4, up to t, and the same for the regressor x. So we're going to observe x at period 1, 2, 3, up to t. Okay, so we're going to have a collection of outcomes and regressors for each unit over time, and then we're going to have that for many units. Okay, so for I going to from 1 to n. Okay, so that's what the data looks like. And then, of course, we need to make some sampling assumptions, right? So we're drawing samples from a population. So what assumptions are we making? We're going to assume that units are going to be IID. Okay, so basically, we're going to assume that, say, counties are drawn from the same population independently. Okay, but then within each county, let's say, we're not going to assume independence. Okay. Statistically speaking, we're going to allow for dependent, non-identically distributed observations within the county. In practice, what does that mean? Well, you know, in statistics, we always want to impose some sort of independence between observations, right? Because that's what lets us kind of like apply laws of large numbers, central limit theorems, estimate variances, conduct hypothesis testing, and so on. But then in this case, if we think about what we have, it's like we have, say, one county that is followed over time, okay? So we have observations for county 1 in periods 1, 2, 3, 4, etc. It would be a pretty strong assumption to assume that the same county is independent of itself over time, right? Because it's just the same county, okay? So we're not going to assume that the observations over time for the same county are independent, okay? We're going to allow for the observations for each county to be correlated over time. Okay, same if we're following, you know, a household. Okay, so, you know, we follow a household in different periods. We're going to allow for these observations to be correlated over time. In economics or econometrics, we call that serial correlation. Okay, just because we think that the assumption of saying, you know, each household is independent of itself over time, that's way too strong. Okay, and if you assume independence where you don't have independence, then your standard errors are going to be incorrect. So we want to kind of like avoid that case. Okay, so summarizing our sampling assumptions, we're going to assume that units are independent of each other. Okay, so different, say, counties, one county is independent of another county, but within counties, observations, we're going to let them be dependent and maybe non-identically distributed. Okay, this will become a little bit more clear later when we talk more about variance estimation and standard error estimation. Okay. Before I move on, any questions about the setup? Okay, great. Again, feel free to interrupt at any time. So let's start talking about fixed effects models within an example. Okay, and so the example is the following. Let's say that we want to analyze whether studying more hours increases test scores. Okay, so let's say we have a data set of students, and these students take a bunch of different exams over time, maybe in a quarter or a semester or a year. Okay, so we see students taking exams at different points in time, and we measure the test score of each student in each exam. Okay, we index, so students by I, exams or time periods by T. So we measure the test score, and then we ask each student how many hours they spent studying for each exam. Okay, so we want to analyze whether studying more hours actually increases test scores. Okay, one could hope that it does, but it's something that we would need to verify in the data. Okay, so what can we do? Well, the simplest thing we could do is like, okay, let's choose one exam, say the first exam that everybody takes, and say, you know, everybody's taking this first exam at the same time. Okay, so we collect data on like each student for this first exam, what test score they got, and what how many hours they studied, and then we just estimate a linear regression. Okay, we can always do that, right? So we open R, do LM YX, or you open Stata, you do reg YX. Okay, so we run this regression by OLS. Okay, standard regression where you have the outcome here, we have an intercept. Okay, so the constant, which is basically what would be the predicted outcome if the regressor was equal to 0. And then we have the regressor, which here is hours of study, and then obviously the error term that captures kind of like everything else. And in most cases, when we run a regression, what we want to learn about is this coefficient beta. Okay, and ideally, we would like to interpret this beta as a causal effect, right? So it's like, if I study more hours, will I see that my my test scores increase? Okay, so we estimate this regression based on, say, a single exam. Okay, the first exam, and we estimate this regression, and then maybe you remember this from your statistics class, or maybe you don't, and that's fine. But whenever you run a regression that looks like this, and you estimate this coefficient here, I'm going to call it beta hat short. Okay, short because it's a short regression that doesn't include any additional covariates or anything else. The beta hat short, so the coefficient from this short regression, will always approximate in large samples this object right here. Okay, hopefully it looks familiar. If it does, if it's not, that's not a problem. Okay, basically beta hat short in large samples will approximate a measure of association between the outcome and the covariate. Okay, more precisely, this measure will be the covariance between y and x, basically measured like, you know, do y and x tend to move together? So if x increases, does y tend to increase or decrease or stay the same? Divided by kind of like a measure of the scale of the regression. Okay, so this beta hat short will approach in large samples this measure of association between test scores and hours. Okay, nothing surprising here. Okay, and you could just run the regression and maybe say, okay, I'm done. That's what I want. Okay, why is that? Well, this is just saying, if, you know, when hours tend to increase, test scores tend to increase, decrease, or stay the same. Okay, depending on what value we get for beta hat. Maybe let's say that you actually run this regression and you get a number that is kind of like close to 0. Okay, so maybe that beta hat is, you know, like a very small number, maybe it's insignificant, statistically speaking. Okay, say, well, that's kind of counterintuitive, right? We thought that actually studying more should increase test scores, right? So that's what we hope. At least, you know, those of us who teach classes would hope that, you know, when people study more, they do better. Okay, but then the question is like, well, is this beta hat really capturing what I wanted to capture? Okay. We said we would like to measure kind of like the effect, quote unquote, the effect of hours of study on test scores. This is not really an effect, right? What we said is like we're capturing as an association between hours of study and test scores. So we need to think a little bit more about what we think the model is, okay, to decide whether we can interpret this beta hat as estimating the effect of hours of study, or maybe it's capturing something else. Excuse me. Okay, so then every time you run a regression, you look at the coefficient and you think, is this what I really wanted to capture? Okay, so let's think a little bit about what we think is actually generating the outcome. Okay, it seems natural to think that different students will have what I would call different test-taking skills. Okay, what is that? Well, it's capturing the fact that, you know, some students are like just like naturally more comfortable taking exams. Okay, and maybe some students get stressed, or they find it harder to focus during an exam because they're nervous and so on. And I'm going to call that test-taking skills. Okay, and this fact is basically saying that, you know, even if we forced everybody to study for 0 hours, different people would get different test scores. Okay, again, one reason would be because, you know, some people are just more comfortable taking exams, so they tend to do better for the same number of hours of study. Okay, so if we want to incorporate this idea of test-taking skills, we could introduce, we could think of a slightly more realistic or more complex model that could look like this. Okay, so in this slightly more realistic model, we again have the outcome, which is our, which is a test score. Again, we have an intercept, okay, and we have hours of study, which is correct, its corresponding coefficient. I'm going to call it beta star. And then we have this additional term that we just mentioned, which is test-taking skills with its corresponding coefficient. Let's call it gamma star. Okay, so then in this more realistic model, we would say beta star is capturing how much we think test scores would increase with an extra hour of study, holding test-taking skills constant. Okay, so for people with the same test-taking skills. And similarly, gamma star would measure how much we expect the test score to change for people with higher test-taking skills, fixing the number of hours of study. Okay, so we may think that this model, let me clean this so it looks a little bit better. Okay, so now we consider this model here. Okay, and maybe that's a more realistic representation of what determines test scores, but that is not what we estimated, right? Remember, what we estimated was this short regression where we only included hours of study. So then the question is, if we run this regression of test scores on hours of study, but we know that there's an additional variable that is test-taking skills, then what are we actually estimating with this short regression? Okay. If we estimate this short regression, but we think that actually there's another variable that we should be controlling for, but we are not, how bad can this be? Okay, well, for that, what we do is we take this result here. We say that this result is always true. Okay, so anytime you run a regression, as long as that variance is not zero, so the ratio is well defined, you will always approach this magnitude. And you don't need any assumptions on the error term or anything. Okay, as long as you can run the regression, this is the number that you're estimating. So then the question is like, what is the interpretation of that number? Is that number capturing something that you want? Well, you can show, and it's actually pretty simple. What you do is you just plug in this more realistic model here, and you replace that here and do a little bit of algebra. And what you find is that this beta hat short, so the coefficient from the short regression that only includes hours of study, will approach this term here. Okay, so that's a combination of two different terms. What is it? It's like, well, the first part here is beta star. And we said beta star is the coefficient from this regression. That is the expected change in test scores after changing hours of study, holding test-taking skills fixed. Okay, so that would be kind of like what in this simplified setting we interpret as kind of like the effect of hours of study. Okay, so that's what we would like to learn about. But that's not all we get, right? We get beta star plus this additional term that is highlighted in red. Okay, so when we run the short regression, not including SI, we're not getting the effect of hours of study, we're getting the effect of hours of study plus something else. This additional term is sometimes known as the omitted variable bias. Okay, why do we get this bias? Well, because we have a variable that we said is part of the true model, this test-taking skills, but we're not including it, we're omitting it. Okay, so we have an omitted variable, sometimes also known as lurking variable. Okay, and so what does this omitted variable bias look like? Well, it's a combination of two terms. Okay, the first term is gamma star. What is gamma star? It's just coming from here. Okay, so it's basically the coefficient from the variable that we are not including. So this gamma star, remember, we said it's kind of like the effect of test-taking skills on test scores. The second term in this bias is just a measure of association between X, which is the variable that we are including in the regression, and S, which is the variable that we omitted from the regression. Okay, so it's basically a measure of association between the variable that we include in the regression and the variable that we omitted from the regression. Okay, so then if we think that actually the number that we were after is this beta star, we are obviously not getting that beta star by just running the regression of test scores on hours of study. Okay, instead, we're getting beta star plus an additional term, which is this omitted variable bias. So let me again clean this. Okay, and so then now we can think, remember I said, oh, maybe you estimate this short regression here and you get a beta hat that is close to 0. And that's a little bit surprising for you because you thought that more hours of study would result in a higher test score. But actually now we see, well, maybe that's because beta hat is not estimating beta star. It's estimating beta star plus the omitted variable bias. What direction do we think this bias will take? Well, we need to think about basically the sign of gamma star and the sign of this association, right? Because this is a product, so the sign of this product will be determined by the combination of the signs of the two terms. In this setting, we may expect that gamma star is positive, right? Why? Because gamma star is here, and we may think that people with better test-taking skills will have higher test scores. Okay, so we may think that gamma star is positive. Okay, so this term here is positive. What about the covariance between S and X? Well, it depends, okay? It's hard to know, but we may think, for example, that this covariance is negative, right? Because maybe people with better test-taking skills are more confident and they need to study less for the exam. So the more test-taking skills you have, the fewer hours you study. So then this covariance would be negative, okay? And that means that then this whole term is a positive number times a negative number, so that would be negative. Okay, so in this case, when we run the short regression, but we are omitting the S variable here, then the beta hat would be an underestimate of the effect of hours of study, right? Because we get beta star, which is the effect of hours of study, minus something else. Okay, so we would be underestimating beta star. Okay, so again, if you run this regression and maybe that beta hat is close to 0, and that seems a little bit counterintuitive for you, maybe the problem is that you have an omitted variable bias because you're not controlling for test-taking skills. Okay? Before I move on, any questions, any clarifications?
Can you please just like sum it up quickly because it's a little like confusing?
Yeah, sure. So what I did is basically I started here, okay? And I said, we're interested in learning whether studying more hours increases test scores, okay? And you said, well, you know, we have data on test scores for a bunch of students at a certain exam, and then we ask them how many hours they studied, and then we run a linear regression of test scores on hours of study. We estimate this beta hat, and this beta hat, as I said, always approaches this term, which is just a measure of association between hours of study and test scores, okay? That is useful in practice, okay? Could be a useful descriptive statistics saying, oh, you know, people when, higher hours of study are associated with higher test scores, but that's usually not what we are looking for, right? Because in our papers or projects, we usually try to get something that looks like a causal effect, right? So we would like to say not only hours of study is associated with higher test scores or lower test scores, etc., but we would like to claim that that is some sort of measure of the effect of hours of study. Can we interpret this beta hat short as the effect of hours of study? Not really, right? Because we may think that actually the short regression is failing to account for other differences in students, for example, the one measured by test-taking skills. So if you fail to account for these differences, what you estimate with the short regression is not the effect of hours of study, but the effect of hours of study plus a measure of the association between hours of study and test-taking skills multiplied by the coefficient of this omitted variable. Okay, so basically, what is this short regression doing when we only include X? Okay, it's saying, well, I'm going to change hours of study, okay, and see how test scores vary. Okay, but so in the data, that means basically compare students that study more to students that study less and see how different their test scores are. Okay, that's kind of like the mechanics of this short regression here. But then what is that comparison capturing? Well, it's capturing first the fact that if you study more, maybe you increase your test scores. But also when we compare students that have different hours of study, these students are also different in their test-taking skills. Okay, so the overall effect of changing hours of study is a combination of the actual effect of hours of study plus the fact that when you increase hours of study, that is associated with lower test-taking skills, and that changes the outcome. Okay, so with this short regression, you cannot kind of like disentangle these two effects. Okay, you cannot disentangle the true effect of studying more from the fact that different hours of study are associated with different test-taking skills. Okay, so we're not getting the effect that we wanted here. In this particular case, we may actually think that we are underestimating the effect. In some other examples, you may be overestimating. In some examples, maybe you don't have any bias, but that will be very context specific. Okay, so that's hopefully a summary of the problem. Basically, you know, this is just omitted variable bias. Okay, so if you should be controlling for stuff and you're not controlling for it, then what you estimate is not what you wanted to estimate. Now, what do we do about this? Can we do something in practice to fix this problem? Well, in some cases, this could be super easy to solve. If we could actually measure test-taking skills for each student, we could just control for that in the regression and run the regression of the outcome on hours of study and this measure of test-taking skills. Okay, that would be great. That would be the easy solution. The problem is that in most cases, this variable will be unobservable. Okay, and this is kind of like one of the most like the hardest challenges in regression when you want to just use linear regression to measure a causal effect or some measure of effect. We will talk about what I mean by causal effect later. The main problem is that we will almost always be omitting some variables that cannot really be measured, either because they're not inner survey or they're kind of like inherently unobservable. Okay, but in many cases, we're going to see variables that we don't observe in our data set. Obviously, if we don't observe it, we cannot include it in the regression. Oops. Okay, so then just including SI will not be an answer for us because we just don't have enough information in our data to do that. So then what do we do? Well, one thing we could do, which is something that I kind of like implicitly did here, is to assume that SI doesn't change over time. Okay, let's say that students differ in their test-taking skills, but those differences are constant over time, at least in the period that we're looking at. Okay, let's say we're looking at students over 1 year, okay, taking a bunch of exams. It seems reasonable to think that your test-taking skills are not going to change too much between different exams within the same year. Okay, so let's say that this SI varies across students, which is why it's indexed by I, but it doesn't change over T. So for all exams these students take, their value of S is the same. Okay, if we're willing to make that assumption, then we can rewrite this model here by just putting, so I'm going to come back here. I'm going to put these two terms together. Okay, which is what I'm doing here. I'm just collecting these two. Okay, this alpha plus gamma star SI, I'm going to call them just alpha I. So then now the regression that I have is test scores on hours of study. And now I have this alpha I, which is very similar to the one that I had here, except that now alpha I changes for different students. Okay, so it changes over I. So this model is a little bit more realistic, right? Because it's just saying now for 0 hours of study, so if we replace this by 0, then we still have different intercepts for each student. Okay, so basically saying like, even with the same number of studies, on average, different students would have different test scores. Okay, and this is what we call a fixed effect. Okay, so as soon as we add this alpha I here, then now this is what we call a fixed effect model. Okay, a fixed effects model is a model that allows for different intercepts for each unit. Okay, so instead of having this simple regression here, what we do is that we add an I here and we say each student will have its own intercept. Okay, so kind of like different students start from different baselines. Okay, that is a way to rewrite our model.